Hello, this is Miss Moore, and today during chemistry we're going to discuss periodic trends, again, specifically ionization energy and electronegativity. Today's essential question: how is ionization energy and electronegativity affected by periodic table location? Okay, a quick warning about today's lecture. Ionization energy and electronegativity are confusing because they're similar but different. So I highly suggest you really think about this lecture. Pause, rewind often. Make sure you understand the difference between ionization energy and electronegativity. All right, we're going to start with a little tiny discussion about ions. An ion is an atom with an electrical charge. Now, if you remember the definition of an atom has no charge because it has equal numbers of protons and electrons. But an atom can have a charge. But once it's got a charge, it's no longer an atom. It's now an ion. Okay? So atoms are usually neutral, no charge, because they have equal numbers of protons and electrons. So if an atom loses or gains an electron, it can become an ion with either a positive or negative charge. And if an atom loses an electron, remember, they used to have the same number of protons and electrons. So if it loses an electron, it has an extra positive. So it's going to have, if it loses an electron, it's going to have a positive charge. And if it gains an electron, it now has a more negative, so it has a negative charge. The octet rule and ion formation. Noble gases. The noble gases are the group 18 elements. So that would be like helium, neon, argon, etc. Okay? Noble gases are really, really stable, which means they are not very reactive. Okay? They're really stable. All atoms want to be really stable. In fact, all atoms do what they do to become stable. So noble gases aren't very reactive because they're already stable. And if that's a little confusing, don't worry about it. We're going to spend a lot of time talking about that next unit. Okay, so noble gases have what we call an octet of electrons. Octet meaning 8. So valence electrons. So they all end, almost all of them end in S2p6. 2s2, 2p6, 3s2, 3p6 in the outermost energy level. And if you remember, only the S and P can be valence electrons. So basically, noble gases have the maximum number of valence electrons, which is what makes them stable. Helium's a little different. He is 1s2. Even though he doesn't have an octet, he's still super stable because he has the maximum number of valence electrons for energy level 1. Energy level 1 only has the S sublimate. All right. So the octet rule. The octet of electrons, the 8 electrons, makes these not atoms, not electrons, makes these atoms very stable. This is because there are no empty orbitals. So the actual octet rule is in forming compounds, atoms tend to achieve the electron configuration of a noble gas. Again, the goal of every single atom is to be just like a noble gas. That's what they work for. Okay? Elements form ions, they gain or lose electrons, so they can become like a noble gas following the octet. Okay, let's now talk about ionization energy. Before we proceed, quick warning. Things get a little tricky right now because we're going to be talking today about ionization energy and electronegativity. And while the truth is ionization energy and electronegativity are completely different, their definitions sound very similar, but they're exactly opposite. So you need to really think about this. All right. So ionization energy is the energy needed to remove an electron. Okay? It is the amount of energy needed to remove one of the outermost electrons, creating an ion. Those are the valence electrons, right? Outermost electrons, valence electrons. Ionization energy is the difficulty of losing an electron. Think of it as how tightly an atom holds its own electrons. Okay, so how it holds its own electrons. Okay? So the tighter an atom is holding its electrons, the greater amount of energy that's going to need to be used to remove it. So there's greater ionization energy. The looser an atom is holding an electron, the less amount of energy it's going to need to pull it away. Okay. If an atom loses an electron, it becomes what we call a positive ion, known as a cation. So ionization energy is the amount of energy needed to create a positive ion. And again, to get a positive ion, you are losing an electron. Okay, so now that we know what ionization energy is, let's talk about the periodic trends in ionization energy. So if you think about it, ionization energy should decrease as you go down a group. This is because the power of the nucleus decreases going down a group, and it does not hold its electrons as tightly. So it gets easier and easier to remove an electron, right? It gets easier to remove an electron. Ionization energy increases across the period. Remember, go back to the power of the nucleus. Because the power of the nucleus increases going across the period, it's holding its electrons more tightly. It gets more and more difficult to remove an electron. Okay? So if we were to make our cute little periodic table, okay, not really very good. That's okay. Going down a group, ionization energy decreases. It takes less energy because we've got the nucleus is weaker. Going across, ionization energy increases, meaning it gets more and more difficult to remove an electron. Why? Nucleus is getting stronger. All right, formation of cations. Remember, cations are the ones that lose an electron, they're positive. So we were just speaking of this. Energy is needed to remove an electron, creating a cation. Because metals have low ionization energies, they lose electrons fairly easily. Think about this. If you're thinking about sweeping across the period from left to right, ionization energy increases. And the metals are more on the left-hand side. So basically, they have lower ionization energies. So important point here, metals become cations. If they're becoming cations, what are they doing? They're losing electrons, okay? So it's pretty simple to determine the number of electrons a metal atom will need to lose to become a cation with a noble gas configuration. Remember, the whole point of atoms doing anything is because they want to be like the noble gases, right? They all want to be S2P6, noble gas, S2P6. Really important. So let's take an example. We have sodium, 1s2, 2s2, 2p6, 3s1. The nearest noble gas configuration is this guy right here, right? Because we have the S2P6. So that's right here. All right, so now, how many electrons must sodium lose to achieve that configuration? 1 electron. He's going to lose the 3s1. So when sodium loses an electron, remember sodium used to have 11 protons and 11 neutrons, right? Sodium had 11 protons and 11, did I say neutrons? Sorry, 11 electrons. If he loses an electron, so he now has 10 electrons, what does he have extra of? A proton. So he's going to be positive, and we're now going to symbolize him as Na1+. Na1+ is now a new term here, isoelectronic with neon, meaning sodium ion, the Na1 plus, has the exact same electron configuration as Ne. Okay, let's try another example. Let's take calcium. Please, please, please try to go through this example ahead of me, if possible. Try to predict what I'm going to do. See if we can turn calcium into an ion. So the electron configuration for calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay? And calcium wants to be like a noble gas. He's a metal, so he's going to be losing electrons. So where is the nearest noble gas configuration? Keeping in mind, noble gas configuration is Noble gas configuration is S2P6. So the nearest noble gas configuration is right there. And that would be argon. So how many electrons does calcium have to lose? 2. So he's going to be Ca2+, and he is an isoelectronic with argon. All right, let's discuss electron affinity or electronegativity. Electronegativity is the ability of an atom to attract and hold an electron. Okay, the definition is the exact opposite of the definition of ionization energy. Electron affinity is the ability to gain an extra electron. I like to think of it as how well an atom can steal electrons, how strong it is. Okay. So when an atom gains an extra electron, it's now got more electrons than protons, so it becomes a negative ion known as an anion. So you can think of electronegativity as the amount of energy needed to create a negative ion. And remember, that means it's going to be adding electrons. All right, I want to give you a quick little analogy. It's not the best analogy, but it might help. We'll see. All right, so we've got ionization energy on one side. And then we'll talk about electronegativity. Okay, so I think of ionization energy as looking at the strength of the victim. Okay, and I think of electronegativity as looking at the strength of the thief. Okay, what they both want, by the way, is electrons. Okay, that's the hot commodity in the atom world. Okay, so the strength of the victim is that, think of that as the ionization energy. So a strong victim would be holding his electrons really tightly. He's really hard to steal from. It takes a lot of energy to steal from him, right? Strength of the victim versus electronegativity. You're looking at the strength of the thief. Who's going to be better able to steal something? Just grab it. Grab it out of the little atom's hands. Well, a strong thief, right? So ionization energy, looking at the strength of the victim atom, the guy that might be losing an electron. And electronegativity is looking at the strength of the thief atom, the guy trying to steal an electron. So who's going to be best at holding on to his own electrons? Who's going to be able to, not be a very good victim would be a strong atom, right? A strong atom would not be a good victim. It'd be too difficult. Who would make a good thief? Well, a strong atom. A strong atom would make a good thief. A strong atom would not make a good victim, right? Okay. So now let's talk about the periodic trends in electron affinity or electronegativity. Again, remembering that electronegativity is basically the ability to steal electrons, okay? So who's better able to steal electrons? Strong atoms. So as you move down a group, electronegativity, or the ability to steal electrons, decreases. Why? Well, the power of the nucleus decreases. Remember, as you go down a group, you're adding more energy levels, more shields, blocking the outer electrons from the nucleus, so the electrons are not held as tightly. Electronegativity generally increases as you move across a period. Why? Well, the nucleus gets stronger and stronger and stronger as you move from left to right across the periodic table. This is because you're adding more protons to the nucleus, and at the same time, you're not adding more shields or more energy levels. Okay? So now let's do our little overview periodic table thing. Looks something like that. So, going down and across, when we're talking about electronegativity, the ability to steal electrons, electronegativity decreases. Going down, right? Why? Weak nucleus. Right? So these guys down here are going to be bad thieves. Put the F and the S in the wrong place. Are going to be bad thieves. Okay? Electronegativity increases. Going across. Why? Stronger nucleus. Sorry, let's do that in yellow. So these guys over here are good thieves. All right, there you go. That is the periodic trend in electronegativity. Okay, folks, I know this was a long one, but this is the last topic. Formation of anions. So recall, electronegativity is the ability to create a negative ion. Remember, electronegativity is the ability to steal electrons. More electrons, get extra electrons, you have a negative charge, you're called an anion. Okay, so if you think about the trend going across the periodic table from left and right, the electronegativity, or the ability to steal electrons, increases. So that means, and the nonmetals are on the right side of the periodic table. So nonmetals have relatively high electronegativities, which means they're pretty good at stealing electrons. So, important point here, nonmetals become anions. Okay, just like if you remember back to way long time ago at the beginning of the lecture, cations come from metals, anions, or the negative ones, come from nonmetals. Okay? So it's pretty easy to determine the number of electrons a nonmetal atom will need to gain to become an anion. With, remember, the whole point of anything an atom does is to become like a noble gas if possible. So we look at electrons configurations again. So we're going to take sulfur for an example. We have 1s2, 2s2, 2p6, 3s2, 3p4. So where is the nearest noble gas configuration? Remembering he's going to become an anion, gaining electrons. Well, remember noble gas configuration is going to be something like s2p6, right? This guy has 4, so we'd need to make that a 6. Okay, so here is the nearest noble gas configuration. And by looking at the periodic table, you should be able to tell who that is. Okay, so how many electrons must sulfur gain to achieve that configuration? Well, we just wrote it on the slide before. 2 electrons to become 3p6. When he gains 2 electrons, he's now going to have a negative charge, right? He's going to be S2 minus, not just S, because S is the atom symbol. S2 minus tells you that he's got 2 extra electrons, two extra negative charges. So now, sulfur ion is isoelectronic with argon, meaning that the sulfur ion has the same electron configuration as argon. Okay, really almost done. Let's try one more, and hopefully you can try it by yourself. So see if you can come up with the type of anion phosphorus can be. So hit pause, try it, and then we can go through it together. Okay, so phosphorus has an electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. So remember, he wants to be s2p6, and he's going to do that by gaining electrons because he's very electronegative. So we could add 3 electrons here, right? And that'll give him 3s2, 3p6. So he'll be 1s2, 2s2, 2p6, 3s2, 3p6. So he is now phosphorus with a 3 minus charge and is isoelectronic with argon. Okay, we finished. Have a good night.